I think the foremost question that must be answered is simple. Is this actual evidence for the existence of a parallel universe? What's going on, smart people? I'm sure a lot of you have come across these articles floating around on Facebook where they're making claims that NASA has found evidence for parallel universes. Well, today I'm joined with Ibrahim Safa. He is a Ph.D. student at the University of Wisconsin-Madison and a fellow at Harvard University. First of all, Ibrahim, thanks a lot for agreeing to speak with me today.
Thank you so much for having me. Good to be with you.
Absolutely. Okay, so you co-authored one of the papers that some people are pointing at and using as evidence for this parallel universe theory thing that's going around. Is that correct?
Right. That's
So,
true. Yeah.
at some point, in just a bit, I'd like to delve into the contents of that paper and have you kind of just describe what it's about, what the research entails, as
hmm
well as the other paper that's kind of pointing at it and using it as evidence. But first, would you mind talking about what it is that you're researching to begin with?
Sure. So what I study are neutrinos, and neutrinos are a fundamental particle. They are the most abundant massive particle in the universe, and they constitute basically a lot of the radiation density in the early universe. So they're very important for studying the early universe and how it started. They're very relevant for any nuclear reaction. So I kind of, an intuitive way to think about it is neutrinos are like nuclear shrapnel. So anytime you have a nuclear interaction where the nucleus is breaking apart or it's changing in some way, there's a neutrino either absorbed or emitted. And so they're very important in our understanding of fundamental physics because they have peculiar properties that actually don't align well with what we know about physics.
Okay.
And so that's why I study them. I work on a specific experiment that studies very high energy neutrinos that come from outside the Earth. So we detect uh, neutrinos coming from outside of our galaxy, and from accelerators that are normally would be black holes or merging giant merging systems. So that's essentially what I'm interested. I'm interested in the high energy neutrino
Mm.
part of it.
That's interesting. So they're extremely prevalent in both the nuclear processes that we're trying to better understand. I mean, that's my field of research is nuclear physics, but also you just
hmm
mentioned these things on the cosmic scale, these things that are created out in the cosmos. That's so they permeate all of physics. Now you said
hmm
that they have some peculiar properties. What kind of properties are you referring to?
So, I mean, it's not peculiar in reference to everything else we know. The weird thing about them is that they have mass, and it's weird because they're not supposed to have mass. So under the standard model, which describes perfectly well everything else that we see, with the exception of gravity, um, neutrinos are not supposed to have mass. And what we did find was this was back in, this was hypothesized as early as neutrinos existed, but it was discovered in the 90s. In the late 90s, it was confirmed that neutrinos oscillate. So what that means is that you create a neutrino or emit a neutrino at a certain flavor, and by the time it arrives to your detector, it has transformed into another flavor.
Mm.
And so that is only possible if neutrinos have mass. So you could think of it as if all of the neutrino flavors are, if they mix, that means that you can have a superposition of neutrino states that travel together, and it's kind of like a wave front. And if one of them is more massive than the other, then there's going to be some interference, and then one flavor can just
Mm.
switch to another flavor depending on where you are in the wiggle, let's say. So we discovered that neutrinos oscillate. That meant that neutrinos have mass, and that doesn't fit well with the standard model. So something needs to be fixed about the standard model, basically.
So we keep bringing up the standard model. Can you talk a bit more about what that is?
Yeah, so the standard model is a description of all of the interactions of the particles that we know of, the fields and particles that we know of. So it's a single equation that describes up to, I mean, I don't know what exactly the precision is, but I know it works over 50 orders of magnitude in scale, and that's the most successful theory I think that we've come up with apart from quantum mechanics. And the way it works is it's just a single equation, and it describes the weak force, the strong force, and the electromagnetic force. And so yeah, it tells you how all the particles get their mass, how they interact with each other, and like I said, it works remarkably well until you get to the neutrino part of it.
I see. So, in the standard model, if you think about the other things like the electron and the other generations of the electron, like the tau and the muon, as you go from electron to muon to tau, those particles get heavier. Is that the same for the neutrino? Or you said that there's a discrepancy between their masses.
Yeah, so it's a little bit tricky because that is true in the generational hierarchy. You have electrons are the lightest, and then muons are the heavier sibling, and then taus,
Mm-hmm.
and that goes also the same in the quark generations.
Right.
But with neutrinos, there are three mass states, and there are three flavor states. And we know that each flavor state, so an electron neutrino, uh, basically it talks to the electron, a muon neutrino talks to the muon. So those are the three generations that correspond to the three lepton generations. But the mapping is not one-to-one between flavor and mass, and that's where the oscillation comes in. So,
Mm-hmm.
and actually an electron neutrino is a combination of all three mass states of the neutrino, and vice versa. So there's not a very good I mean, there's a great mathematical description, but uh, we don't really know which, if the lightest neutrino state is predominantly electron neutrino or vice versa. So we know it's one of them. It could either be, that's what it's referred to as the either normal ordering or inverted ordering of neutrinos, because all we can measure are the mass squared differences. So we don't measure directly. We haven't measured yet. We can, but we haven't yet measured because it's so small, the mass of the neutrino. But if you measure the oscillation, you're effectively measuring the mass square difference of the neutrino states. And so, given that we only know the squared difference, that means we don't know the overall sign.
I see.
And so either the flavors are aligned with the mass states, and in that case, it would work the same way as with electrons and muons and taus, or it's inverted, in which way the heaviest mass state would be the nu E
I
state.
see. And
Mhm.
then just for those of you watching, in case certain jargon gets thrown around more than enough, like it's particle physics, it's bound to happen. If we use the word lepton, a lepton is just one of the fundamental particles that doesn't interact via the strong force. Is that correct? Do you agree with that kind of definition?
Yes, yeah.
Okay.
Hmm.
So just in case that word gets thrown about around a bit more. Okay, so neutrinos are important to study because, like you put it, they're like the shrapnel of nuclear processes. Understanding them has a huge amount of insight into how nuclear physics works as a whole.
Hmm.
Uh, some properties of them, I know that they don't have a, even though they do carry a mass, they don't carry much mass. They don't
Hmm.
interact via the strong force. They don't carry an electric charge, or maybe they do. They carry an electric charge of 0. So great, they're important, but how do you measure them in the first place? How do you find them?
Yeah, that makes it really difficult, doesn't it? I mean, they do. Luckily, they do interact via a single force, which is the weak force, and that works on very small scales. So this happens when, like I said, there's let's say you have an unstable nucleus. It decays, and then with that decay, it emits a neutrino.
Mm.
And so what you can do is you can study, let's say, the reverse of that process. So you can have a beam of neutrinos that you make in a lab, and you shoot it at a bunch of isotopes, and then you wait for a neutrino to capture onto a nucleus and change it into a different nucleus. And then you measure that, and you can tell that there was a neutrino that came in because nothing else would cause that process. And so that's one way to detect neutrinos. It's called inverse beta decay. Another way to detect neutrinos is to infer their mass when the beta decay happens. So it's the other way around. So you just put a bunch of radioactive stuff and you wait for them to decay, and then you measure the missing energy, the missing momentum, because the energy of the things that come out has to be equal to the energy that was contained in the nucleus. And so if there's missing momentum, then that's where the neutrino went. And so that's a sort of indirect way. Another way you could do it is if you have a very high energy beam of neutrinos, uh, it could smash into protons. And when it smashes into protons, it destroys them. And so it creates other particles as a byproduct. And so by measuring all these other particles, you can infer that the neutrino has interacted and destroyed the nucleus that you were looking at.
When I think of beams, like in particle accelerators, I think of these huge quadrupole magnets that help focus the beam and make it tighter and tighter.
Mm-hmm.
How do you do that with something that doesn't carry a charge, though? How do you make how do you make a beam of neutrinos? Or is
Yeah,
that
it's
getting
tough, right? So that's one of the biggest uncertainties we have when we make a neutrino beam. So what you do is, it's very cool. You first have to accelerate protons to very high energies, and then you smash them into a block of lead. And we know
okay?
that and we know that when protons, when you smash protons together, you create a shower of particles, and some of these particles are mesons, and those are just like quark anti-quark pairs.
Mm-hmm.
And so the proton is a 3-quark composite, and a meson is a 2-quark composite. So you could just imagine, when you have a bunch of quarks smashing into each other, you're going to create some of these 2-quark paired particles. But those particles are very short-lived and they decay very quickly. And whenever there's a decay, there's a neutrino. So what you do is, you have your protons coming in one direction, smashing into the lead, and then you have magnetic horns that focus the mesons, because even though they're very short-lived, they still go through a little bit of matter, and then they decay into muons and neutrinos. And then those neutrinos are pretty forward, because there was so much kinetic energy going into the mesons, that the neutrinos coming out will be very beamed forward. And so there is kind of a spread to the beam, but it's well measured, I think, to within like at least 20% or so, and at Fermilab, where they have it's called the NUMI beam, where they do this. Mm-hmm.
So you take a beam of something that you can focus, wait for
Mm-hmm.
it to decay, and hope it stays focused by the time you get a beam out of neutrinos. Okay,
Exactly. Yeah.
that's interesting. Okay, so where do these kind of measurements typically take place? Where do you look for these neutrinos?
Well, you have to go to, working with neutrinos, because they're so elusive. That means you have to really control your background. There's so many things that can mimic the signals that neutrinos give, that you kind of have to go to the ends of the world, or to deep mines. And so one example is there's a mine in I believe Minnesota, if I'm not mistaken. So we, experimentalists go and look for these old decommissioned mines, and they put neutrino experiments down there, because you have such an overburden of, like, let's say you have a kilometer or so of rock above you, that anything that can come down at you that is not a neutrino, that interacts more frequently, gets blocked by the rock, and then only the neutrino can make it through, because it interacts so weakly.
I see.
And so the national lab in Chicago, in Illinois, it's called the Fermilab, has a beam of these neutrinos, and they send them out across the states. I want to say South Dakota, and that's where they're building this huge neutrino detector that's going to be 40 kilotons of an inert material, which is liquid argon. And so liquid argon doesn't do anything on its own; it just sits there. But when there's a charged particle that comes through, it ionizes the argon, and you can measure the ionization energy.
I see.
And so, it kicks off electrons, and then the electrons can be drifted, and then you can collect the electrons on wires. And so you wait, you just sit and wait in a place where nothing should give you light. And then when you do get light, you know that is probably a neutrino.
I see. Okay.
Yeah.
So in your let's switch over to your recent paper. I'm just going to share it for a moment just so people know what to look for if they're interested in reading it by themselves. So we have a search for IceCube events in the direction of Anita neutrino candidates. So you were talking about how with any decay comes neutrinos. So it's pretty easy to, I guess, know that you've made some if you have a container of something that decays, but not all neutrinos come from Earth, right? They can come from elsewhere. So
Exactly.
what this
Exactly.
paper, yeah, okay, please
Yeah.
go.
No, go ahead. Go ahead.
So with this paper, you're interested in with particles like neutrino that are so elusive to find, even though that we know that they're there because they're a product of decay, which happens all the time. Whenever you do find some, you'd like to reconstruct where they came from. And one of the large parts of this paper, if I'm not mistaken, was determining the source of where certain neutrino candidates, as you call them, were from. Would you like to expand on that a little bit?
Sure, sure. So what we've been talking about so far are kind of low energy neutrinos. And what does low energy mean? Let me show you. So I'm going to share my screen real quick.
Okay. Oh,
And
perfect.
so And so you see here, this goes from all the way from micro electron volts all the way to 10 to the 21 electron volts.
Jeez.
And these are all neutrino fluxes that are naturally produced. So they can come from, there's the C nu B. So this is left over from the Big Bang. This, on the very left, this gray line.
Okay.
It has not been detected yet because it's such low energy that we don't have the technology yet to do it. But there's a bunch of experiments working on this. There's a solar neutrino flux because there's nuclear fusion happening in the sun, and that's actually what confirmed that nuclear fusion was the driving mechanism of star activity, is by detecting these neutrinos. There's terrestrial neutrinos, so those are just like uranium and thorium that is just in the earth, that is unstable, just decays every once in a while, and you get this flux of neutrinos from. And then you have, the supernova 1987A, which was, when a star's life is over, it explodes sometimes, depending on how massive it is. And actually, we think that the neutrinos are the drivers of this explosion. And actually 99% of the energy of a supernova is emitted in neutrinos. And so there's a huge flux of neutrinos that comes from explosions of stars. And then you have atmospheric neutrinos. These are neutrinos created just because we have, for some reason that we don't quite understand yet, we have very high energy protons smashing into the Earth, coming from all directions. And when they do that, it's the same way that you would that we were describing with the beam. It's like smashing a proton into lead. Protons with these energies don't make it through the atmosphere. It's like smashing them into lead. So they create neutrinos, and those shower down on us, and we detect those as well. And then you get to the far end of the spectrum at the highest energies, and those are extragalactic neutrinos. And those are really rare. We see an IceCube about 10 per year. Under a background of hundreds of thousands of events every year. And so we don't know exactly where these are coming from. We know that they have to be coming from places where there is a lot of potential energy, because there's no thermal process to explain this. There's nothing that you could, nothing in the standard model you can write down that tells you that you can get such an energetic neutrino. But we know that there's so much energy contained just in the gravity and the potential around black holes. And so black holes could accelerate protons, could act as accelerators. And then these protons could get beamed and then smash into matter or clouds or radiation, and then create these high energy neutrinos that we see. And so that's basically all of the natural sources of neutrinos that we know of.
Yeah, I'd like to make a couple comments on this if you don't mind. So,
Sure.
let's see. So right around here, I guess, is where LHC would sit, right? That's about 10 to the 13 eV. That would be around the energy of the protons that the Large Hadron Collider can output.
Yeah, so 10 to the 12 or 10 to the 13 would be the energy where the LHC accelerates to. Yeah.
So, but these AGN and GRB, GZK, it seems like nature's way better at building particle accelerators than we are. We've got some
Yeah,
catching up to
well,
do.
exactly. Yeah, so we see an ice cube. Normally, it's about 1,000 times higher in energy than you would be able to create in an accelerator.
My next question is about these little, what looks like oscillations. These look like resonances to me. Is that, what are these? These little
Are you talking
oscillations here?
about the solar
Solar and
flux?
terrestrial, I just see little spikes and then it goes back down and then more spikes.
Yeah, well, I think that's caused just by a decay spectrum. And so these are, you're seeing in the solar, for example, this is a decay chain that produces a spectrum of neutrinos.
Okay.
And then at some point, a new decay chain kicks in, or a new fusion chain kicks in. And so some of these are just protons on protons. Some of these are when you create carbon or nitrogen. And those are very well predicted. The shapes, why they look like this is very well understood. But it's just, it's a threshold thing. You're just going from one process to another.
I see.
Yeah.
Okay. Well, that clears up my confusion. So, in you and your collaborators' paper, there's a lot of reference to two particular detectors, IceCube and
Hmm.
Anita. Can you
Yeah.
distinguish between those two for me?
Right. So to put some context here, these neutrinos are really rare. If you see, we're talking about around 10 to the 15, the flux is about 20 orders of magnitude below the solar flux, right?
Right.
So we're looking at extremely rare processes, and to do that, you need huge detectors. Because all we do is just put light detectors somewhere dark and sit and wait for one of these neutrinos to come. And so the larger your detector is, the more likely one of these interactions will happen while you're waiting. And so to detect these astrophysical, we call neutrinos, we had to build the IceCube Neutrino Observatory. And this observatory is in the South Pole. The reason it was in the South Pole is because there's a cost factor that has to come in here. You can't just build a vat of 1 billion tons of material and expect it to be funded. So even back in the 60s, when neutrinos were just discovered, people were coming up with these ideas of using natural bodies of water or ice, to have a way of having a transparent medium that you could just cheaply instrument with light detectors, and then you just wait. And so let nature do the work of building your medium for you. And so they found this Antarctic ice, which was ultra pure, and it's actually the result of thousands and thousands of years of pressure. So 1.5 kilometers below the surface, the ice crystal structure is nearly perfect. And so a photon can travel about 100 meters before it scatters off of anything, which is insane. And so that enabled the construction of this relatively cheap detector, where you just you dig a hole in the ice. Actually, you just use a water drill, so you just pump hot water into the ice, and then it's not powered by anything. You just let it fall, and then once you have a hole of water, you then drop these photomultiplier tubes. So those are like light bulbs in reverse. Instead of turning electricity into light, they turn light into electricity. And so you put them into the holes, and then you wait for the water to refreeze, and then you do that 86 times. And then you build this array of a 1 kilometer cubed of ice, which kind of looks like this. So what you see here, these strings are where these photomultiplier tubes are, and each dot is one of these photomultiplier tubes. And then the IceCube lab is on top, which is it's this one. So this is the lab where all the computers are, and these are the wires that come in, just that transfer the data. And so this is the lab here in on top, and then this detector is buried about 1.5 kilometers to 2.5 kilometers below the surface. And we essentially just wait for things to come through the Earth. Like you see here, there's this nu mu in dashed blue. And this nu mu comes in. When it interacts, it makes a muon, and a muon kind of makes a track of light in your detector. And so if you see nothing and then suddenly a track of light that's coming up through the Earth, then that's definitely a neutrino. And so, yeah, this is just for scale. You see the Eiffel Tower here in comparison to this detector, because it's so hard to explain this sometimes, the scale of this. But this is a massive
Wow.
detector.
That's incredible.
Yeah. So the light here, the colors show you time. So red is earlier, blue is later. So that's how kind of we visualize this data. And then the size of the bubble is how much light was deposited. So the more light there was there, the bigger the bubble looks.
Are those then like scintillators or something?
They're just photomultiplier tubes.
Okay.
So what happens is, the muon is traveling faster than light in ice, and so it causes something called Cherenkov radiation. Basically, radiates a cone of blue light. You can kind of think of it. It's not a direct analogy, but you can kind of think of it as breaking the sound barrier. Is when you break the sound barrier, you have this cone in front of you. And so the same thing kind of happens when particles are traveling faster than light in a medium. And so we just wait for these cones of blue light to come through.
And you look at like the angles for that helps with particle identification, right?
Exactly. So different particles leave different signatures. So a muon leaves a track, and the timing tells you where it was coming from, right? And so you can reconstruct kind of where the angle was, and then the amount of light is a proxy for how much energy it had.
Now, is IceCube sensitive to detecting these at particular energies, or is it just a wide spectrum of what it can register?
Yeah. So IceCube has sensitivity from about 1 GeV all the way up to about 10 to 100 PeV. And so that's on this plot here, that's from about 10 to the 6, 10 to the 7, all the way up to about 10 to the 17 or 16 or 18. Yep.
Okay. So from atmospheric up to anything cosmic.
Yeah.
Cosmic related. Okay.
Mm-hmm.
So it sounds like that sounds deliberate, because it sounds like you're filtering out the solar and terrestrial neutrinos, or is that just happenstance?
Right. Well, the goal was to measure these cosmic neutrinos, and we've managed to measure them. Yeah. There are experiments that are designed just to detect solar neutrinos, and they're very good at doing that. But you have to what you have to balance is how big your detector is. What material do you put in there to like optimize certain processes and stuff like that.
Okay.
Yeah. So where IceCube loses sensitivity, so where we stop seeing things, is around 10 to the 18 or 10 to the 19. That's because, these events become the scale of these events becomes even larger than our detector. So we can't really see them. They're not being contained. We cannot see the process happening. And so what you need even bigger detectors than that. And then you run into more problems because you're hitting also here a cost limit. And so what people have come up with are these very clever ideas of also using natural bodies of in the Earth, such as the entire Antarctic continent. And so that's where Anita comes in. And so this Anita basically is a helium balloon that is attached to a bunch of radio receivers. And it flies above Antarctica. And what they do is they just fill it up with helium. They have the hard drives and their triggers ready, and they just send it up. And it goes around in a circle around Antarctica. I don't think they have much control over where it goes. It just follows the wind.
Mm-hmm.
It just happens to be because it's at the South Pole. It's circular, and so it goes around a couple times, and then they can they crash it basically whenever it's getting close to where they want it to land, and then they send someone out to collect the hard drives, and hopefully the payload is safe. So what they do is they look down, and they use effectively the entire Antarctic ice sheet, and wait for these radio showers to come up from the Earth. So that's basically like effectively using more volume to detect higher energy processes.
What's producing the radio waves?
So it's called Ascarian emission. It was discovered by a guy named Ascarian, and and what it does is like at a certain point your shower is so big that a shower of charged particles is emitting electromagnetic waves at all frequencies, right? But the only frequencies that can escape are frequencies that are on the scale of the size of the shower.
Oh,
And so those are the waves that interfere constructively, and then everything below that interferes destructively. And so the radio waves happen to be the ones that interfere constructively, and so you get this front of radio waves coming from these showers.
And from when I was going through your paper, it seems like you can distinguish between whether the radio waves is coming from the Earth or whether it's coming away or coming towards the Earth and reflecting off of the ice. Is that correct?
Right. So that's what Anita. Yeah, that's what Anita does. So IceCube does not have the capability to detect radio waves. It only detects visible light. But Anita can figure out what direction it's coming from based on the polarity of the radio wave. So it's known that these, when a neutrino interacts in the ice, it creates a charged particle, and that charged particle, as it's propagating, when it decays, creates this radio shower. And so that radio shower has a specific polarization when it's created. It's vertically polarized. And so if you see a shower coming up that's vertically polarized, it's more likely to be, it's more likely to have originated inside the Earth rather than coming down from the atmosphere. Because, these cosmic rays that I told you about, they extend all the way to these highest energies. And it can create a shower that then reflects off the ice, and then you would see it as upgoing. But the only difference is that when it reflects off the ice, it flips polarity.
Okay.
So you see it as horizontally polarized.
Okay. So that sounds like a great way of determining where the source is. Is it coming from space, or is it coming from the center of the Earth?
Well, I think what they want to find is skimming neutrinos. So those are neutrinos that are not necessarily going through the Earth, but that are just barely touching the Earth to interact like once, and then you see it coming up, basically. But it's like skimming the Earth, coming from space.
Ah, okay.
Mm-hmm. But that's what they're searching for.
So you're searching for these. I think you call it cosmogenic.
Cosmogenic, yeah.
Cosmogenic neutrinos.
Mm-hmm.
Okay.
Mm-hmm.
So in the paper, you referenced that you were kind of using IceCube data and Anita, not quite in coincidence, but you were looking for neutrino candidate detections from both IceCube and Anita, plus some lag time. Can you tell me why you were looking for signals from both of these detectors?
Yeah, so the peculiar thing about what's called the anomalous Anita events was that they were not skimming; they were coming from about 30 degrees below the horizon, and that meant that the neutrino had to go through about 6,000 kilometers of ice, of Earth, and that's not possible at these energies. So as you go higher in energy, the cross section increases, right? So the probability of a neutrino interacting increases with energy. And so at these energies that Anita is interested in, the neutrino should interact within 100 kilometers, about half the time. And so if you see something that has gone through 50 times as much matter, that's problematic because it's just not supposed to do that. And the probability for it to do that is about 1 in 100 million. And so that's why they were labeled anomalous, because they looked like neutrino showers, or showers caused by neutrino interactions. They had the right polarity, but the direction was not, in accordance to what we expect. And so when you're confronted with something like this, of course you have to test all possible reasons for such an event. And one of these possibilities was that maybe there's a very, very intense source of neutrinos somewhere outside our galaxy that's just beaming these 10 to the 19 or 18 neutrinos at us. And if that's the case, then you would only see them coming from one direction, right? And so if that's true, we should point IceCube in that direction and see neutrinos coming from there. And that is because of an effect that's called, tau regeneration. So if you want to just break this down a little bit, like we said, there are 3 flavors of neutrinos. One of them is the tau neutrino flavor. And when that interacts, it creates a tau. Now, the tau is very short-lived. It's about 10 million times shorter lived than the muon. And so it decays very quickly. And so when it decays, it gives you another neutrino, right? And in that process, you only lose about you only lose 5/6 of the energy. So you're left with a large fraction of the energy that you started with, so the tau doesn't lose a lot of energy. So what you're doing is you're cascading these neutrinos down. They start at 10 to the 18 or 10 to the 19, but by the time they get to your detector, they're at energies that IceCube can detect. And so that's something we discovered while we were working on this problem, trying to see what we could do in order to use IceCube as a way to either confirm or deny the interpretation that these are neutrinos. And so what we found is that, if you have a flux of these neutrinos coming through, every time one of these high energy neutrinos escapes, there's about 1,000 other neutrinos at lower energies that have to be coincident with it.
I see. So
right?
That's that secondary wave?
That's the secondary, that's the secondary wave of neutrinos, because you have a high energy beam and it's cascading down, and every once in a while, you can kind of postulate, every once in a while one of these high energy neutrinos will just escape without interacting. And so if that's the case, then there's 1,000 other ones that we should see in IceCube.
So just to put it all together, so for your paper, the anomalous neutrinos, Anita detected some neutrino candidates that were very, very high energy at a particular angle, which made it seem like they went straight through the Earth when they shouldn't have, right? So then you point IceCube in the direction to see, well, where did they come from? Let's look in that trajectory and see if we can find a source. Maybe, I don't remember if it's I don't know the difference between quasars and blazars. Apparently, it's the angle that they're pointing. I don't know.
Yes.
But whether it comes from something like this, a point source that's directed at Earth. Now, you think it was initially coming from a source because there was no angular distribution that was seen by Anita. It wasn't constant over the angle that Anita was measuring for these neutrinos. Is that what happened?
Right. So if it's coming from everywhere, then you would expect to see the ones coming this way. If this is the Earth, you'd expect to see ones coming this way to come before the ones coming this way, right? Because the probability of this happening is much higher than the probability of that happening. So that kind of ruled out. That was another paper by Peter Gorham and collaborators where they made this argument and they ruled out that this could be what we call diffuse, which means it's coming from everywhere, flux of neutrinos. And so the only other possibility under standard model assumptions was that it's a point source.
I see.
Mm-hmm.
So it's unlikely that it came from the center of the Earth. It looks like it would come from a certain point source in a certain direction. Did IceCube find the source?
No. So that's the main result of our paper, is that we looked and we tried a couple of different ways, time dependent or time independent. No matter how you spin it, there are no events coming from that direction.
Oops. I see.
Yeah. So there cannot be a point source in that direction.
So either, I think as you put it, maybe there's something that we don't quite understand about the Antarctic ice, but there is possibility that there's some very new physics to be learned from all of this, because you can't quite explain it with the standard model based off of what we understand about how neutrinos behave. So that welcomes some new ideas. Right? And then I suppose that brings us to the next paper of discussion that kind of took you and your collaborators' results and came up with a hypothesis about where, let's see, that's not that. I think this is.
Yeah. So while you're pulling that up, there's several explanations, right, that people have come up with. You could invoke dark matter. You can invoke things called sterile neutrinos. You could invoke axions, which are another dark matter candidate. And so there are many explanations that could be posited to explain these events. One of which is also ice. But let's talk about this, and then we can talk about the other explanations.
Okay. Yeah, that sounds good. So upgoing Anita events as evidence of the CPT Symmetric Universe. So in the media, from what they've been publishing in these articles, I think it all, for the most part, stems from the second page here. And I've seen quite a bit of clickbaity, where the hell are you getting this interpretation from results? I've made plenty of videos of me getting triggered based off of people just trying to take things out of context. In my opinion, what I've seen from these Facebook posts and stuff, I can't really say I blame them for getting that out of this paper, about saying that there are parallel universes. We go to the second page here. It says, we frame our discussion for context. This is a letter. For those of you who haven't been exposed to too many scientific papers, letters are typically a good amount shorter than full papers. So this is a pretty short paper. But that's not because they didn't do their due diligence necessarily. It's just because it's the nature of these kinds of papers that are published. But these individuals took the results from you and your collaborators' paper and interpreted it in a certain way. And if we go to the second page, it says, we frame our discussion in the context of the CPT Symmetric Universe. In this scenario, the universe before the Big Bang and the universe after the Big Bang is reinterpreted as a universe-anti-universe pair that is created from nothing. That sounds an awfully lot like evidence for parallel universe, if your results are evidence of this. So can you talk a little bit about what this paper is trying to say, and why they're claiming that your results, your measurements, are evidence of this CPT Symmetric Universe, whatever that is?
Well, when you talk about evidence in a scientific context, there's a statistical statement that you're making. And I think, this idea of a CPT symmetric universe goes back several years, and it's on its own, it's not entirely crazy. There's just no evidence for it. And to call our results evidence of the CPT symmetric universe, I think, is a bit of an exaggeration. What our result was refuting any standard model explanation, but it lent no specific evidence to any beyond standard model explanation. So, of course, you can interpret this as saying this could be dark matter. This could be a CPT Symmetric Universe, but you have to back that up with, predictions. So a good theory not only explains what is seen, but also predicts things that you can measure in the future, right? And so this idea of a CPT Symmetric Universe has very specific implications. And in fact, one of the more important predictions is a massive dark matter particle that's about 500 PeVs in energy.
Jeez.
And so, right, and so that's. So not only do you have to posit that this particle exists, right? You have to also hypothesize that what we saw was evidence for it, which I don't think is a proper claim. But you also have to say that this dark matter that they are saying is causing this signal is distributed in such a way in the Earth that it's not falling into the center, but it's like on a disk of if you go to the little schematic they have
Sure.
in this paper. So you see right there, you see that gray shaded region in the Earth,
Oh,
right
yeah,
there.
I do.
Yes. So that's where the dark matter has to be. Otherwise, this doesn't work, right? So if it was normally distributed, like you would expect any gravitationally falling matter to behave, then it would all be concentrated at the center. But if it was concentrated at the center, you wouldn't see the signal. So you say, all right, I'm going to now play with the distribution of this dark matter until it gives me the signal. So now not only do you have to explain why does dark matter, just because there's a dark matter particle in the Earth, even if there is dark matter in the Earth, that doesn't tell you that there's a CPT Symmetric Universe, right? So there's several leaps of faith that are being taken here to get to a cool and very interesting idea of a CPT Symmetric Universe, right? So you have to explain this anomaly with dark matter. This dark matter has to be distributed in such a way that it's very specific way. So that's what we call fine tuning sometimes, when you're trying to just like tune a model
Sure.
so that it fits your data. And then the consequences of this, so you look and you say, all right, so now we know what the dark matter is, right? This is 500 PeV dark matter. That's what the dark matter is. So let's go look at the galactic center. And, because we know there's dark matter there. And so if we look at the galactic center, we should see these neutrinos coming from the galactic center, right? And we don't. And so there are several, it's a very neat idea, but there are several holes in this particular framing of the idea, right? So the original paper that talks about a CPT Symmetric Universe does not talk about it as proven or as there's evidence for it. It postulates it from first principles. And so, I think it's fun to talk about this, but to call it evidence, to call what we saw evidence, is an exaggeration, to say the least.
Completely unrelated, but what this kind of reminds me of is like when you go to solve Einstein's field equations, you're not free to choose necessarily what the distribution of matter and energy is. That's typically the given. Like if you were to solve any problem in Gauss's law, it's like, here's the distribution of charge, how does that affect the field? Or in field equations, it's like, here's the distribution of matter and energy, how does that affect the space-time metric? But then what some people do is they solve the problem backwards. They say, I want this to be my space-time geometry. What does the matter and energy distribution have to look like in order for this to be my answer?
Oh yeah.
It's a bit of a stretch analogy, but that's just the little cartoon that came.
Oh no, it works. And there's all sorts of ways to do phenomenology, to try to explain phenomena that you see, and this is one of them, right? Reverse engineering is a great way to do it. But then you have to go about and explain what this means. What are the implications of this, right? What else do you expect from this sort of universe that you just created? And there's nothing of that sort in this paper, right? Like you said, it's a letter, and so maybe there's more to it. that didn't make it in the letter, but from what I see, there's not much to back it up.
Something that I should have asked you a few minutes ago actually is what does CPT symmetric even mean?
So CPT symmetric. So there is a concept of a CPT symmetry for particles and fields. So we know that well, to the best of our knowledge, particles obey CPT symmetry, and that just means, the C stands for charge, and P stands for parity, and T stands for time. So there's a symmetry under charge, meaning if you exchange a particle for its antiparticle, that's effectively that's an exchange under charge symmetry. If you exchange parity, that means you're mirroring the particle. So there's a thing called handedness, right, in the standard model, and so we know that there are such things as right-handed and left-handed particles, and so P is simply a mirror image of the particle. So if you exchange a particle for its antiparticle counterpart and for its other handed particle, and it's going back in time, it acts the same way as you would expect. So just to put this as an example, an electron's anti-particle is a positron. So you can describe an interaction of an electron, and then if you exchange that electron, you write down that equation, and you exchange that electron for a positron that is right-handed and going back in time, you get the same laws of physics. And so that's what CPT symmetry is. But that only applies to particles, right? So the idea of a CPT symmetric universe extends that to the entire universe and says the universe is CPT symmetric, and it's trying to kind of like aiming to solve a problem that we've always known existed, which is that time goes in one direction in our universe. And so one way to solve that is to say, well, it goes in one direction here, but it goes in the other direction in the anti-universe. And so you have this, you build the symmetry where you have a universe and anti-universe pair. And in one universe, time is going this way, the other universe, time is going the other way. But that is just a way to represent it. I don't think, time wouldn't be going backwards necessarily. It would be going forwards, but you would have antimatter instead of matter, let's say.
But they would probably call us the antimatter.
Yeah. I mean, that's just a matter of
yeah, exactly. Difference, like what things are is different from how we describe them. Right.
And so it's a beautiful idea. The idea of charge symmetry, for example, it means that positive doesn't mean anything. Positive is just what you call positive, and negative is just the other thing, right? And so there's no significant meaning to positive and negative. It's just the opposite of each other.
Ben Franklin had a 50% chance of getting it right, and he got it wrong. That's how it was explained to me. Okay, so, I think that more or less answers most of the questions. So, this is a really cool idea. I was exposed a little bit to CPT theorem when I took, particle physics. And when it was introduced to me, it seemed kind of like this universal, that was already something no one really argued with. We'd found evidence of CP violation, thanks to the weak interaction, because it violates every symmetry that it can, which is why I stay as far away from the weak interaction as I can. But so far as I know, I don't know of any processes that violate CPT symmetry. So extending that, so calling something a CPT symmetric universe, I was like, well, yeah, obviously it is, because nothing
sure.
Individually.
Yeah. And it explains everything. That's it's great. You just have to tell me what I need to go look for to prove that it exists, right? And then I'm happy to do it. Crazy ideas are what we start with. We know that what we have, the description of physics that we have is incomplete, and all we do, and I'm sure you do the same, is try to find new ways to explain phenomena that we know, or trying to find new phenomena to explain in new ways, right? And so these ideas are wonderful, right? We follow them, and anytime there's an anomaly, that's why there's so much interest here, is because we saw something we didn't expect, and that's where you discover things, right? But it's important to differentiate that from evidence, right? speculation and evidence are very different things.
Sure.
Yeah.
So I think the conclusion is, no one's shooting down CPT Symmetric Universe theory, but using the results from you and your collaborators' paper is probably not appropriate to do.
Right. So the more, if I could just tell you what the more reasonable explanation is.
Oh, sure.
Um, the ice that I was talking about that was ultra transparent in Antarctica, right, happens at about a kilometer below the surface. Above that, the ice is still, as you go up near the surface, it's more fresh and it's newer ice, and so it hasn't had time to compress, right? And so the ice at the very top, like 100 meters or so, is called the firn. And this is actually a paper by Shoemaker et al. That explained the possibility of this reflection that can happen, but due to these peculiar properties of the ice, you have non-uniform ice basically. So you might have some pockets of air, some pockets of denser ice in places, and so it could reflect in such a way that it wouldn't flip the polarity, and it would give you a vertically polarized upgoing signal.
Mm.
And so, when faced with these two explanations, I think you often use Occam's razor and say, well, it's probably the ice unless we can prove otherwise, right?
So it sounds like we may not be in a CPT Symmetric universe. We may just be in a universe where our approximations aren't good enough about the ice. So,
right, those are the two possibilities.
Awesome. So, do you have any time for some questions? I polled some of the viewers of my channel if they had any questions they'd like to ask. If you don't mind, if we went through a couple of them. If you have
Yeah,
time?
absolutely.
Cool. I won't
Yeah,
put them on
I
this
could-
screen because I don't want to risk doxing anybody.
Oh, that's
but,
that's fine.
just
Yeah,
so that we
sure.
can read them together.
Yeah.
So, do these
Okay.
results potentially indicate something is missing from the standard model?
hmm And perhaps, yeah. So like I said, yeah. I mean, it's not only these results. It's just the existence of massive neutrinos tells us there's something missing from the standard model, and this is yet another, hint. But like I said, it's more likely the ice, and until we disprove that it could be the ice, we cannot say for sure that this work that we did is evidence for new physics. But there has been many, like I said, proposals. This person seems to be well read in the literature because they list axionic dark matter, sterile neutrinos, supersymmetry, and heavy dark matter. So these are all explanations that were posited, and not one of them is more compelling than the other, right? They're all possible explanations, and we just have to study the ice better. And if it tells us that our approximations were correct, then we can look more closely at these.
So, when you say different explanations, is it meaning like, oh, what we measured wasn't actually a neutrino? It could have been one of these other exotic forms of matter. Is that?
Yeah. So if you think about this problem, it's a problem of propagation through the Earth, right? So you have to get this neutrino through the Earth somehow. So one way to do it is to say, it could be a sterile neutrino. So sterile neutrinos don't even interact weakly, but they still oscillate into these active neutrinos. And so you can tune your sterile neutrino mixing parameters such that the chord length that it has to pass through is about the length it needs to transform from a sterile neutrino into an active neutrino. And then that in turn interacts and give you a signal. So that's a possible explanation. Supersymmetry is invoked because you can have things called staus, and that's the supersymmetric partner of the tau. And these staus lose energy, lose a lot less energy than the taus. And so you can kind of say, okay, well, maybe it interacted, created a stau, and a stau doesn't lose its energy very often, and so it managed to escape the Earth. And so that's the kind of gymnastics that you have to do.
That's interesting that we're spending all this time wondering where the neutrinos are coming from, and then one of the other questions is, are we sure it's a neutrino?
Yes.
Okay. Do you think that the use of science as a political tool encourages the sensationalist misrepresentation of researchers' findings? I like that question a lot.
Yeah, absolutely, it does. Like one thing I can think of as recent is this whole debate about hydroxychloroquine, where it was just like someone saw some correlation that was not statistically significant. That was like, we gave these patients some hydroxychloroquine and they got better. So that doesn't imply that it was the medicine that caused it. That just implies there's some correlation there, right? And that more studies need to be made. And so that work was sort of saying, this is interesting. We should study this more. And what ended up happening, because it was politicized, is we have now two groups of people who wholeheartedly believe that hydroxychloroquine will cure COVID-19, and people who think it's whatever you want to say, it's a hoax, or like it's manufactured. And neither of those things are true. We still don't know, scientifically, whether there's any real evidence that this is a good medication. So it totally helps politicizing things. Totally helps to misrepresent researchers' findings.
It's in a sense it's a bad thing, or maybe it's doing a good thing for the wrong reason. I mean, I'm sure they got a lot more funding to research this compound than because
Right.
it became so popular.
And it forces us to be more careful, right? As
Mhm.
scientists, when you are publishing a work, then there are, now you have political pressure on the inside of the scientific community that is kind of pressuring you into like um, being as conservative as possible about what claims that you make,
Mhm.
right? Which is good ultimately for science. So that helps, that we don't just go out and say, "Hey, I found this thing," or "This is," because we know how it could be interpreted by the public, and so it forces you to be more careful in representing yourself.
Yeah, I think specifically, like everyone who publishes, for the most part, everyone who publishes papers also gets it on archive first. If
Hmm.
you can look on the margin here, it says archive, and for those of you watching, that's kind of like a free distribution platform for people who are publishing papers, but want it also available that's not behind a paywall. So, in a sense, anyone who has access to internet can read papers that are published on archive. That includes the general public, whereas people who only publish on distribution platforms that require a
Hmm.
subscription, be it through a university or whatever, I think maybe it's okay to use the words that are okay to use in your field because, well, the media is not going to pay to go read your paper. But if it's just available, yeah, maybe you should be a bit more careful with the words that maybe there's more of a liability on our end, like you said, to be more
Exactly.
careful with how we communicate this stuff.
Exactly. Yeah. Hmm.
Uh,
Exactly right.
I like this. I think the foremost question that must be answered is simple. Is this actual evidence for the existence of a parallel universe?
No, I wish. I wish it were. I would be. Here's the thing. I would be the first to come out and say it. This would be that would be the end of my like career, right? I would just hang back and enjoy discovering a parallel universe. I would be doing nothing else. But this is not actual evidence for the existence of a parallel universe. Uh, Although, maybe in a few years, if this continues to be, Anita has flown one more time, and they still have a batch of data that they haven't released, and they claim that this time they have a better understanding of the ice. So maybe in the next couple of years, if this continues to be an issue, it becomes more interesting. But so far it's not actual evidence.
So one person asks, how do you feel about the coverage that the paper has gotten in the popular science slash mainstream outlets?
I don't know how it was a roller coaster of emotions. I have to say, because this paper is like 8 months old, and in academia, that's you've already moved on, right? You're working on something else. And we got some press attention at the beginning when we published this, but then it died down, and then I was like, all right, we're done with this. And then all of a sudden, I see this Sun article that had a quote of me in there, and it said that there was evidence for parallel universe. And then it was at first it was just amusing, and then as it started getting traction, I started getting nervous. And then the New York Post made an article about it, and I was like, well, now something's happening. And then we had this amazing communications director. I'm lucky to have like people who know this field to help me. But like Madeline O'Keefe here in Madison, reached out to these outlets and told them to remove any mention of my name. And the Sun obliged, but the New York Post just ignored us, and that's when I got angry. And then the next day I wake up and it's all over the place, and it's like a top trending topic, and I'm just, yeah. So it was, I think in the end, people responded to it in the correct way. And we're lucky to be living in a place where you have Twitter, and you could just directly interact with the people they're claiming to quote, instead of just relying on some news sources. But yeah, it was a roller
actually
coaster.
how I found you. It was in some article, and someone was quoting your tweets where you were like, our what is it? How you communicated? Maybe we don't really understand the ice as much as we did, but maybe there's some new physics. The media, parallel universes must exist. It was great.
Yeah.
Okay, so just a few more. So one person says, and I'm sorry if I'm butchering the name of the co-authors' names, but one says, Artson et al. Says in their conclusion that the upgoing showers could be caused by other effects and not necessarily produced within the Earth, whereas Ankardoki et al. Conclude that it's definitely coming from within the Earth. Who's right?
I think the burden of proof lies with Ankardoki et al. If they're claiming that it's coming from the Earth, then they have to prove that it's coming from the Earth. Mm-hmm. All we said was we don't know where it's coming from, and it can't be a neutrino that we all know and love. So I think ours is a negation and theirs is a claim, and so you have to prove a claim.
I like that. That's perfect. This clears up some things, but why was everyone talking about time flowing backwards? Great question.
Yeah, we talked about this a little bit, yeah, and that that's the big mystery of is one of the big mysteries of our universe, is that time goes in one direction, seemingly, on large scales. And so you would naturally assume, if there's this CPT symmetry that we talked about, that this other universe would be exactly the same, but with time flowing backwards. But that's not particularly accurate, because time is just a measure of change. And so something cannot be unchanging. So the time will flow in the same direction, but it's the C and P that will be flipped in that universe. Right. So I think exactly. And the time flowing backwards is just a popular way of saying it, or a headline way of saying it.
I'm glad you bring that up. Yeah, so for like CPT symmetry, what you switch the charge, you switch the parity, and then you make time go the other way. The claim is that nothing happens. You get the same particle that you started out with.
Right.
Another way of phrasing that is saying, if I switch the charge and I switch the parity, that's equivalent to then switching time, because that's like switching time and then switching time back. So
yes,
I mean, maybe there are some subtle arguments with what I just said there, but that's another way. It's a matter of semantics. How are we describing these things?
Exactly. Yeah.
Is there anything we can be doing to stop the media taking these things out of context? It's incredibly frustrating. I like that this question doesn't immediately blame the media. It's like if we're publishing papers, it's up to us on how they're communicated. I think that's the issue. If it's freely available to everybody, because we're putting it on an archive, let's be very careful.
Exactly. And I think it was a combination of things. It was us saying that it can't be a standard model neutrino, and then it was the other paper saying blah 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 as evidence. And so when you use words like that, those are buzzwords for reporters. And I think the onus is on us to be more careful with what we claim. But when you see something like this, when you see a media headline, I mean, there are telltale signs, right? If the author of the paper only has a half a sentence in the entire article, then they've been taken out of context. You can just conclude that, right? Because the reporter is not going to frame the scientific argument better than the scientist they're talking to. Another thing is like, if you see these are spawning articles and they're not necessarily citing anything, right? So this New York Post article cited the Sun, and the Sun cited New Scientist, and New Scientist cited itself, and it was like there was no scientific paper in there,
Yeah.
right? And so that's another telltale sign that it's been exaggerated if the sources don't have the actual work in them.
Yeah, there was it's when I was going through the clickbaity articles, I was
Hmm.
it was incredibly hard to find the one that you did, and when I found the one that you did, I thought that was the one they were talking about, and I was like, where the hell are they getting parallel universes from this? And then when you and I got to talking, you pointed me at the other paper. But yeah, there should be more accountability, like not to just point
Exactly.
fingers at the media, but I mean, I'm not aware. Maybe that's an education thing. Maybe we should know what people are allowed to say about our work. I don't know what the legal ramifications are for misrepresenting someone else's data or someone else's publication. If I were to talk badly about you and say things about you as a person that's absolutely not true, and that could be defamatory or whatever the word is, but
Exactly.
I
Exactly.
don't know if that kind of thing exists for making conclusions about someone else's work that isn't true, for someone else's
Yeah,
science.
I'm not quite sure, especially like quoting me for something that had nothing to do with, like, it was a totally different paper that was claiming this. And then, you're harming let's say I apply for a job to work at a national lab, and then they Google my name and they see 10 articles with my name in them that are claiming that there's a parallel universe. That
Yeah.
harms me in the future, right? And so these things, I'm not sure if there are laws to protect against this. I certainly don't know of them if they exist, but you know, evidence that we emailed them and they didn't even respond means that they probably don't care, or they have a team of lawyers, and
Mm-hmm. Well, what you're doing is incredibly proactive because you putting yourself and your science and emphasizing that on things like Twitter, where you directly interface with maybe people of the general public who aren't as into science as you are, that just makes the communication of what's really happening easier to do rather than having to. I mean, who watches the news as much anyway? I mean, everyone's on social. That's where people are getting this in the first place, is social media.
exactly.
So
Yeah.
it's like, unless you want to reach out to these articles and hope that they'll be on your side of taking your names off of things,
Hmm.
places like Twitter where you can say for yourself, this is actually what was done is incredibly important. So,
Exactly. So I think, yeah, that's another important part, is establishing a direct connection with the public that is, independent of the media, so
mhm.
that you can just talk to people. And I think that's a new thing that we have. We should use it.
Yeah, absolutely. Well, Brahim, I
Hmm.
really appreciate you taking the time out of your day to talk with me. So if you guys are interested in following Brahim and seeing what he's up to with his neutrino physics, you can go ahead and follow him on Twitter on what is it? It's Ibrahim Safa 1, I think.
Hmm.
I'll post a little thing up here somewhere. Is there anything
Yeah.
that you'd like to say before we end this?
No, I really enjoyed talking to you, and yeah, thank you for having me on. And I'm happy to talk to you about physics anytime.
Yeah, likewise. This was good. It was educational for me. I had a good time, and it's good with these kinds of articles to not just immediately make up your mind and discount what people are doing because they have an out there theory. It's nice talking to someone like you who's pretty open minded about this kind of thing. Like you said, it's not inherently crazy. It's just maybe not real evidence
Right.
here.
Exactly.
So,
Exactly. Yeah.
anyways, thanks again for speaking with me, and I'll talk to you soon.
Thank you. Bye bye.